Hey there, it's Parametric Myers, and today we'll be checking out section 15.5 called Parametric Surfaces from the Calculus text by Larsons and Edwards. So my name is, like I said, Parametric Myers, and I wrote the guided notebook that you're seeing here. So let's warm it on up by finding the unit tangent vector, t at t, and we want to find a set of parametric equations for the line tangent to the space curve r at t equal to 2 sine t, 2 cosine t, 4 sine squared t at the point 1 root 3, 1. So go ahead and pause the movie. I know you can do it. Warm it on up. And your mark, get set, go! Okay, let's see how you did. So first of all, let's go ahead and find that unit tangent vector t at t. So to find, just to remind you, t at t is going to equal to r prime at t over what? Beautiful, the magnitude of r prime at t. And so we'll have our t at t is equal to, so r prime at t will give us what? 2 times cosine at t, and this is a vector, and negative 2 sine at t. And then, using the chain rule, don't forget, we're going to have 8 sine at t, cosine at t. And that will be over r prime at t. So we'll have the square root of each of these squared. So what will that be? 4 cosine squared at t plus 4 sine squared at t plus 64 sine squared at t cosine squared at t. Okay, so now we're going to have the unit tangent vector at t is going to be, let's see, we can factor out a 2, and we'll be left with cosine at t, negative sine at t, and then 4 times sine at t times cosine at t. And that will be over the square root of 4 times cosine squared at t plus sine squared at t plus 16 sine squared at t cosine squared at t. Just factoring out a 4 from each term. And once I bring that 4 out, that's going to be the square root of 4, so it'll be 2. So it will divide out the other 2. So we will get the unit vector at t will be equal to cosine at t, negative sine at t, and then 4 times sine at t times cosine at t, all over. Now the cosine squared at t plus sine squared at t will just be 1. So we'll have the square root of 1 plus 16 sine squared at t times cosine squared at t. And remember, that was this here is how we got the 1. Groovy? Okay, so now you're probably saying, well, hey, where do I plug in the 1, the root 3, and the 1, right? Well, note that since all 3 are positive, right, we're going to be in the first octant. So I just need to find the angle that satisfies all three components. So just looking at the first one, do you see that 2 times sine at t, that's like our x at t, has to equal to 1. So that means that sine at t has to equal to a half, which means that t has to be pi over 6 because we are in the first octant. So notice that, so the first quadrant, on the plane satisfies that. So all three components have to satisfy that, and if you try each of them, you will find that t must indeed be pi over 6. So t at pi over 6. So our unit tangent vector at pi over 6 is going to equal to, well, cosine at pi over 6 is beautiful, root 3 over 2. Sine at pi over 6 is negative a half, is a half, but then we apply the negative sign. And then we'll have 4 times 1/2 times root 3 over 2. And that will be over the square root of 1 plus 16 times sine at pi over 6 is a half, and then you square that and you get a quarter. And then cosine at pi over 6 is root 3 over 2, and when we square that, we'll get 3/4. And so here we go. We will have in the denominator, these 4's divide out the 16. So we'll end up with the square root of 4 in the denominator. And we can definitely simplify a bit. Let's just shake it out and see what we get. Okay? So here we go. So t at pi over 6 will be root 3 over 2, negative a half, and then we will have root 3, because these 2's will divide out the 4, and then that's over root 4, right, which is 2. And so t at pi over 6 will be equal to, so I'm just going to multiply through by a half. So we'll get root 3 over 4, negative 1 over 4. And then now let's find our direction numbers. Let's factor out so we can get our direction numbers. Basically, if we factor out a quarter, we can write that our unit tangent vector at pi over 6 is going to be a quarter times root 3, negative 1, and then 2 times root 3. So this is gonna, so here's our answer to the first part, right? So find the unit tangent vector t at t, meaning at the point 1 root 3, 1. So that's this. And now what's going to happen is we've gotten our direction numbers. So A is root 3, B is negative 1, and C is 2 root 3. And so remember that. So now let's, just use another parameter S for this guy. And if you recall, you would get that x would equal to, your x1 plus your direction number a times s. Y would equal to y1 plus b times s. And then our z would equal to z1 plus c times s. And so this would give us x is equal to x1 was 1, and then a is root 3, so plus root 3 times some s, and then y would equal to root 3 minus s, because b is negative 1, and then z would equal to 1 plus 2 root 3 times s. Groovy? All right, so that's the result for the second part of the problem. So for finding a set of parametric equations for the line tangent to the space curve at the point. Cool? Awesome. All right, so now how do you represent a curve in the plane by a vector valued function? Well, remember, we do this by saying r at some parameter, call it t, is x at t times I plus y at t times j. And then what about a curve in space? Beautiful. R at t would just be x at t times I plus y at t times j. Whoops. Plus z at t times k. Cool? All right, so continuing, we have definition of a parametric surface. Let x, y, and z be functions of u and v that are continuous on a domain D in the uv plane. So the set of points x, y, and z given by r at u and v is equal to x at u and v. So now x is a function of two variables times I plus y at u mv times j plus z at u and v times k is called a parametric surface. So the equations x equal to x at u and v, y equal to y at u and v, and z equal to z at u and v are the parametric equations for the surface. So, in our first example, find the rectangular equation for the surface by eliminating the parameters from the vector value function. And then we want to identify the surface and sketch its graph. So, here we go. R at u and v is equal to 2u cosine v times I plus 2u sine v times j plus 1/2 u squared times k. So let's check it out. We know that x is equal to some x in terms of u and v. Well, in this case, our x is equal to 2 times u times cosine at v. So let's sort of pause here and then look at y is equal to y at u and v. And so y would equal to 2 times u times sine at v. Cool so far? We can go ahead and put that z is equal to z at u and v. So this, of course, would be z is equal to 1/2 u squared, because that's the coefficient to the k. But let's look at the x and the y. Do you see they both have that? They have a cosine at v and a sine at v, and then they also have that 2 times u. So if I square them, so if I squared both sides of those first two equations, right, then I would end up getting x squared is equal to 4u squared times cosine squared at v, right? And then y squared is equal to 4u squared times sine squared at v. Well, x squared plus y squared, if I add them together, that would give me 4u squared times cosine squared at v plus 4u squared times sine squared at v. Good so far? Awesome. So x squared plus y squared will be 4u squared times cosine squared at v plus sine squared at v. And as we're getting so used to now, isn't that just 1? So it turns out that x squared plus y squared is equal to 4u squared. And again, that's because this is 1. Groovy? Now, if we go ahead and if we square, if we work with z a little bit, all right? So let's work with z. Would you agree that 2 times z is equal to u squared? Cool so far? So I know that x squared plus y squared is equal to 4u squared, right? If I multiplied both sides by 4 when working with my z, I would have 8z is also equal to 4u squared. Cool so far? So now, putting that in here, I'll end up getting, at the end of the day, x squared plus y squared, well, maybe not the end of the day, is equal to 8z. So now if I isolate z, what's going to happen? I'll get z is equal to 1/8 times x squared plus y squared. So you'll get parabolas in the xz plane, parabolas in the yz plane, right? So it ends up being a paraboloid, right? Let's see what the graph is going to look like. Okay, so there's our paraboloid. Okay, so next up, let's find a vector-valued function whose graph is the indicated surface. So the plane x plus y plus z equal to 6. So if we go ahead and isolate z, we would get z is equal to 6 minus x minus y. Good so far? And so, all right, well, we got to get a function of u and v. So if we let x equal to u, and if we let y equal to v, right, then z would now equal to 6 minus u minus v. So r at u and v will equal to u times I. U is not a vector. U is the function x equal to x of u and v. So, and then v times j, and then z, remember, is all of this. So 6 minus u minus v times k. So kind of one of those so easy it's hard situations, right? All right. So next example 3. Write a set of parametric equations for the surface of revolution obtained by revolving the graph y equals x to the 3 halves, where x is between 0 and 4 inclusive, about the x-axis. So you might have to, look it up a little bit, but if we go ahead and we let x equal to u, then it turns out that y is going to equal to, remember, f of u times cosine of v. That's in our formula. So that means that y would equal to, the f of u would be u to the 3 halves, right? And then cosine v. Z is going to equal to our f at u times sine at v. And so it turns out that z will be u to the 3 halves sine at v. So let's just clean it up. We'll have x equal to u, y equal to u to the 3 halves cosine of v. Z would equal to u to the 3 halves sine of v. And remember that 0 is less than or equal to u is less than or equal to 4. And then we've got to get that revolution of 2 pi, so v has to be between 0 and 2 pi inclusive to get our surface of revolution. Groovy? All right. So example 4. Find an equation of the tangent plane to the surface represented by the vector valued function r at u and v is equal to u times I plus v times j plus the square root of u times v times k at the point 1, 1, 1. All right. So the first partial of r with respect to u is going to be what? I, 1 times I, right? Plus 0 times j, because there's no u's in j. And then we'll have plus v over 2 root u times v times k. That will be I plus, I don't know if you want to rationalize or not. I'm just going to keep it like this. This is fine. Plus v over the square root of u times v times the vector k. The first partial of r with respect to v is going to be 0i plus 1j, and then plus u over 2, sorry, I forgot my 2 over here, 2 times the square root of u times v times k. So that will just be j plus u over 2 times the square root of u times v times k. Groovy? Awesome. Now, how do we find the equation of the tangent plane? I mean, what do we do? Beautiful. You find the cross product. So if we find the cross product of these first partials, that's going to be the determinant of I, j, k. So the first line will be 1, 0, v over 2 root uv, and then 0, 1, u over 2 times root uv. So this is going to equal to, well, depends what you want to expand about, right? It'll end up being, I'll just go ahead and expand about this line, this column, plus, minus, plus, because it's got a 0 in it. So we will end up getting, this will equal to I times 0 minus v over root uv. There's a 2 in there. And then minus 1 times u over 2 root uv times j minus k. And then the last one just zeroes out, right? So then we will have this will equal to negative v over 2 root uv times I minus u over 2 root uv times j plus k. Good so far? Awesomely awesome. So at 1, 1, 1, right? Well, we got to figure out x at u and v is equal to 1, right? From the ordered pair here, or ordered triple, rather. And y at u and v is also equal to 1, right? So, and that's of course from here. So, putting all that together, what would happen? I mean, x at u and v, what did we end up getting? We got here that u was 1, right? And then y is v, and v is 1. So we will have r, the first partial of r with respect to u, cross the first partial of r with respect to v at 1, 1, 1. This is all at 1, 1, 1, will equal to negative a half So I'll just show the work. So negative 1 over 2 root 1 times I minus 1 over 2 times root 1 times j, and then plus k. And again, just plug it in. That's kind of the tricky part sometimes. So that's just going to equal to negative 1/2 I minus 1/2 j plus k. Good so far? Awesome. So next up, let's get our direction numbers. So let's go ahead and just factor out a 1/2. So that would just, or a negative 1/2 we could factor out. And then we'll just get I plus j minus k. And so utilizing those direction numbers, we would have 1. So this gives us that A is 1, B is 1, and K would be actually negative 2, right? Or it would be have a coefficient of negative 2, not negative 1. So C would be negative 2. So we'd have 1 times x minus 1. That 1 is from the order triple 1, 1, 1. And then plus 1 times y minus 1, again from the order triple. And then minus 2 times z minus 1. So the coefficients are the direction numbers, and the in the parentheses, that's from the order triple 1, 1, 1. So that's all going to equal to 0. So simplifying, we would get x minus 1, y minus 1, minus 1, plus y minus 1, minus 2z plus 2 is 0. And so the constants would 0 out, so we're just going to get x plus y minus z is 0, or minus 2z equals 0. And that's the end result. Cool, cool? Okay, so this is a great mix of, a lot of the skills that we've learned in the class. So now the area of a parametric surface. Let S be a smooth parametric surface, R at U and V equal to X at U and V times I, plus Y at U and V times J, plus Z at U and V times K, defined over an open region D in the UV plane. If each point on the surface S corresponds to exactly one point in the domain D, then the surface area of S is given by the surface area is equal to the double integral over the surface ds, which is equal to the double integral over this region D of the cross product, the magnitude of the cross product of the first partial with respect to U and the first partial with respect to V dA, where the first partial with respect to U would be dx du times I plus dx dy du times j plus dz du times k, and the first partial of r with respect to v is going to equal to dx dv times I plus dy dv times j plus dz dv times k. Cool, cool? Okay, so last example of the day. Find the area of the surface over the part of the paraboloid r at u and v equal to 4u cosine v plus 4u sine v plus u squared times k. And that was 4u sine v times j plus u squared times k, where u is between 0 and 2 inclusive and v is between 0 and 2 pi inclusive. So, here we go. Let's do it. We know what we need to find. The first partial of r with respect to u is going to be, so remember that x at u and v will be equal to 4u cosine v. Y at u and v is equal to 4u times sine at v. And z at u and v is equal to u squared. So we will get 4 cosine v times I plus 4 sine v times j plus 2u times k. Cool so far? Now the first partial of r with respect to v will be negative 4u sine v I plus 4u sine v, cosine v j, and then the k term zeroes out. So finding the cross product, or finding, yes, we'll do a piece at a time. So the cross product of these two will be the determinant I, j, k, and then we'll have 4 cosine v, 4 sine v, and then 2u, and 0 for that last one, negative 4u sine v, and then 4u cosine v. Sorry, it's kind of small. Okay. Well, that in turn is going to equal to, actually I'm going to work vertically. This will equal to, I'll go ahead and expand about here, so I'll get plus minus plus. This will equal to k times 16u times sine or cosine squared at v, and then minus minus is plus. We'll get 16u times sine squared at v. And then the next one will be minus 2u times 4u cosine v times I and then minus is plus again, and then we'll have 4u sine v times j. So that will give us, notice that this is 16u cosine squared v plus sine squared v. So that part will just be 1. So we're just going to get 16u times k, and then minus 8u squared cosine v times I minus 8u squared sine v times j. So putting this into component form and factoring out a negative 8, we'll end up with, actually we could factor out a negative 8u, right? And then we're going to have the first component will be u cosine v, and then u sine v, and then we'll have negative 2. Cool so far? So how do we figure what is what? So remember we need to find the magnitude of this cross product. So that's going to be equal to the absolute value of negative 8u, because we were able to factor that out. And then times the square root of u squared cosine squared v plus u squared sine squared v plus 4. And so that's going to be 8u, because remember u goes between 0 and 2, so I don't need to worry about the absolute value, times the square root of u squared times cosine squared v plus sine squared v, and then plus 4. Remember this is equal to 1, so we'll get 8u times the square root of u squared plus 4. Cool so far? So I think we have almost all the pieces, right? So here we go. The surface area will be equal to, we'll have our double integral, and remember we have our 8u times u squared plus 4 to the 1/2, and it's going du dv. And so we're using this formula here. And so now that means u is going, remember, between 0 and 2, and v is going between 0 and 2 pi. So that's going to equal to the integral from 0 to 2 pi of, so I need to have a 2u in order to integrate. So if I just factor out a 4, right, because 8 is 4 times 2, I'll have what I need for the integration. So I'm going to get u squared plus 4 to the 3/2 divided by 3/2, and then that's going from u equals 0 to u equals 2, and we're still going to have to take care of the dv. So now we will have, bringing that, multiplying by 2/3, we're going to end up with 8/3 on the outside. And we'll have our integral from 0 to 2 pi. Notice that our lower limit will not zero out, so be careful. So when u is 2, I'm going to get 2 squared is 4, so I'll get 8 to the 3/2. And then when u is 0, we'll get 4 to the 3 halves dv. We can simplify that somewhat, right? This will be 8/3 integral from 0 to 2 pi. Actually, that's all a constant, so we can take it out. So we'll start simplifying here. So 8 to the 3 halves would be the square root of 8, the quantity cubed. So this would be 2 root 2 cubed. And then minus the square root of 4 is 2, so minus 2 cubed dv. So then we will have, we can definitely bring out a factor of 8. So we'll have 64/3. And then root 2 times root 2 times root 2 is 2 root 2, and then minus 1. And this, sorry, was times the integral of from 0 to 2 pi of dv. It's the integral 0 to 2 pi of dv. So it looks weird, but that's okay. So that's going to give us 64/3 times 2 root 2 minus 1 times v, and v is going from 0 to 2 pi. The lower limit will zero out, so 2 pi times 64 is 128 pi, and then we have it over 3 times 2 root 2 minus 1 square units. Cool? All right, so that's it for today. I hope you have a wonderful morning, afternoon, or evening whenever you're watching this show. And hey, if you like what I'm doing, please subscribe and tell all your friends. Bye.